Hey everyone, we've finally made it to the final video in the Lyra's Locomotion Explained series, where I'll be covering the footplant control rig which handles slope warping for the characters in Lyra. So, let's get into it. Alright everyone, so I wanted to give you guys a brief overview of what the control rig does before we get into the explanation. So, I'm on a slope here, and as you can see, the feet are aligned with the slope perfectly. They're rotated to not be intersecting with this slope rotationally, and they've been raised or lowered so that they do not intersect with the slope positionally. And of course, this isn't something that can be animated into the locomotion animations because that would just be impossible to account for every possible slope and impossible to build a system to, I mean, there's an infinite variety of slopes and it's really just unfeasible. So instead, what is done is that the feet that, well, instead what is done is that the game does multiple traces to determine where some points are on the ground that are needed for a calculation to raise and lower the feet, as well as the surface normal, the pointing direction of the faces of the geometry that the trace hits, to determine how to rotate the feet. And there are a few main traces that Lyra does. The first trace it does is to determine whether or not the character is on a slope at all, where it traces from above the root bone to below the root bone to determine where the ground is below the character's feet. Then it does a trace 25 units in front of the character, from 50 units above the character to 50 units below the character, so roughly knee height, given those 2 points, as well as the normals that those traces return. It is able to determine whether or not the character is on a slope. Knowing that the character is on a slope, the control rig continues, and it does 2 traces from the feet, one for each foot. A trace that takes the foot position, traces from above it to below it to try to find the ground near the foot. It does the same for each foot, and that trace will return the ground and the hit normal of that trace. That ground point is then compared to the location of the foot to get the required offset in the Z direction, so the up and down direction of the world. It does a comparison between the 2 traces, the 2 offsets that it needs to apply to the feet to determine which foot is lowest. It then takes that information and uses it to lower the pelvis by that amount, which will lower the entire character's body down to the point where the lowest foot touches the ground. So now that the entire character has been moved down, it then takes each foot and adjusts it as needed towards the target offset, also taking the new pelvis offset into account with the equation. Then it takes that surface hit normal of each of the foot traces and uses it to rotate the foot that the trace was done from so that it aligns itself with the ground. And that was the simplest manner in which I could think to explain how this control rig works. Of course, it is a little bit more complicated than that, but that's why there's this video, and that's what I'm going to be going through for the rest of it. So, let's get started. Alright, so I am back in the Lyra project, and I have navigated into this rig folder within the mannequin character, and I'm going to go ahead and open up the control rig mannequin footprint rig. And this is the control rig that is being used inside of the main animation blueprint at the very end. If I just head back over into animations and open up the animation blueprint mannequin base, we can see it in the anim graph right here at the end. It takes 3 inputs, a disabled control rig, an is crouching, and a has velocity. So this control rig is divided into 2 sections, a setup section using a setup event, and a forward solve. So the setup event just fires off before it starts solving anything, so it can do any sort of initialization that needs to be done before the rig starts computing everything it needs to compute. So it sets a left foot offset variable from the current transform of the left foot, and a right foot offset from the current transform of the right foot. Then stores the calf and leg length for basic IK nodes, which ensures the rig adapts to different proportions. So it takes these, gets the difference, gets the length of that difference, because the subtraction of vectors will result in a vector, and uses that to set a thigh length variable. It then subtracts the foot from the calf, or my bad, the calf from the foot, and gets the length and sets the calf length, though it could be either way around. It doesn't really make a difference. The end result will be the same. And then finally, it initializes controls to adapt to different proportioned characters. So it sets a control offset for a body control to the pelvis, and a pelvis control to the pelvis, so these two controls here. And then it sets a control offset for a chest control, which is this control here, to the spine 3 bone. And that is it for the setup event. Once it has initialized these variables, it begins to do a forward solve. There are two main sections here. A section that is just gathering info about the world, and a section that is then adjusting the rig based on the data that has been gathered. We're going to start at the top and just obtain an understanding of what data it is gathering. It is getting the transform. So it's doing a bit more than gathering, actually, it looks like, because it is taking the transform for the left foot, and it is setting the transform for the IK foot bones from that initial foot transform, which means that even if the animations being used don't have the IK bones animated correctly, this will fix that and move the IK bones to the locations of the FK bones. And then it is also every update, updating the position of the chest control, body control, the chest control and the body control to the spine 3 bone and the pelvis bone, respectively. Next, it is using two parent constraint nodes, which constrain an item's transform to multiple items transforms. So it is taking the left knee pull vector control, which would be, one of these two controls here, and it is constraining it to the IK foot L bone, meaning that wherever that bone goes, it will keep a relative transform distance from that. Because this rig is just raising and lowering the IK foot bones, it's doing a bit more than that, so I should say that it is the only thing it's doing to the IK foot bones is raising and lowering them, to raise and lower the left and right feet, meaning that if you just maintain a relative transform between the foot and the pull vector control for the knee with the IK, the knee will keep pointing where it needs to point. And for those of you who are unaware, the pull vector is just a vector. If you have an IK chain, you can supply it with, well, for some solvers, you can supply that IK chain with a vector that will tell the chain which direction to bend in, so that the knee will bend forwards, and so that, let's say, the foot is raised, and the knee doesn't bend backwards into a shape that it definitely should not bend in. So once it has done that, it moves on and detects if the character is sloping, and it sets variables accordingly. So it uses a draw slope function, takes in multiple inputs, it does one for the root, and it returns two variables, two values, an is sloping boolean and a slope angle vector. Let's go ahead and take a look at this draw slope function and see how it works. So first thing it does is it uses a sequence node to control the flow of its logic. The first thing it does from that sequence is it sets a slope angle and then sets that is sloping value as well. So it is setting these local variables within the function for use elsewhere. The next thing it does is it draws a bunch of debug shapes if debug is enabled, and if the character is sloping. I'm going to cover each of these in more detail. I just want to give an overview first. And then finally, it returns the isSloping and slope angle local variables. So, to start, let's see how it sets these two local variables. So, the first thing it does is a trace. A sphere trace by channel. It gets the transform of the input bone. In this case, it is the root. It takes that translation and it adds it to the scaled translation of an axis vector input. In this case, the axis is set to 1 on the z-axis, which means that this scale is being, this 1 on the z-axis, is being multiplied by this input hit radius value, which is 50. So, the 1 on the z is being multiplied by 50, because it's a vector, it's taking the z direction from the root, multiplying that by 50, which is going to place a point somewhere up here around the knees. That's going to be the location of this new vector. Now that vector goes into an add node, and it is being added to the translation of the root, because right now this is just a vector with a z value of 50 with this use of the function. Adding it to the transform, the global transform of the root bone, means that we now take the transform of the root bone, that value, raise it up into the air by an additional 50 units, and that is the value we get when we add these together. That becomes the start for a sphere trace by channel, and then we scale this z50 vector by -1, making a z -50. Do the same thing where we add it to the transform of the root bone, and then we do the sphere trace to that endpoint. So we start tracing roughly around the knees and end tracing below the feet. And that trace will return a hit location, and a hit normal. Let's come down to this second trace before we continue forward inside of this function. We get the transform of the root. We add it to a preset offset of 25 on the y and 50 on the z. We also add it to a preset offset of 25 on the y and -50 on the z. And then it does a sphere trace by channel. So this time, instead of tracing straight down from the root, it does a very similar trace, except now this trace occurs 25 units in front of the character. And does a sphere trace by channel. So now we have the results of 2 sphere traces. So the next node here is an AIM math node, which is pretty new to me. I've certainly never used it before. I have not spent much time with the control rig or any control rigs myself. So I'm going to go ahead and read what the comment here says. It outputs an aligned transform of a primary and secondary axis of an input transform to a world target. So essentially, my understanding is that you input some vectors and it outputs a rotation that you can get to rotate one vector so that it's pointing at the other vector. In this case, we take the hit location, so we take the floor beneath the root bone, and we want to rotate that point to get the lookout rotation from that point to the hit location of the trace in front of the character. So, to do that, it takes in the target, and then it takes in the hit normal of this here, and that normal is just the angle, the pointing direction of the surface. So, if I go over into Microsoft Paint of all programs, and I draw okay, it looks like I'm a bit zoomed in here, and I draw in a slope, and let's draw a stick to represent our character on this slope. Now, this right here is the root bone. It has a position in space, and that first trace is going to trace from 50 units above that root bone to 50 units below. And it is going to find a collision point right here. This is that target location. So this is that location variable that is the output from that sphere trace. But we also have a normal. In that normal is the direction of the geometry's face that was hit, the direction it is pointing in. So in this case, if I try to draw an arrow straight out from the surface, we have a vector that is pointing in this direction. So that node takes a vector that it represents the location and a vector that represents the normal of this trace, and using that location and the normal, it figures out what the rotation needs to be to point from this point to the hit point of that second trace, which is a trace 25 units in front of the root from 50 units up to 50 units down. So that's going to hit whatever the surface is there. And so it's going to take in this location, figure out how it needs, what rotation value there would need to be to rotate this location, or to rotate something on it, to this location, and it needs the normal to better understand the context of the situation, I guess. So the output results in a transform, and which includes a rotation, a translation, and a scale. That transform is used to debug, but what is actually used for the calculations is this rotation value, which is a quaternion that gets converted to an Euler. It checks if this rotation value is nearly 0. If that is not true, the local variable sloping is set to true, because if this outputs an angle, it means the character is on a slope. The only way it would output an angle less than 1 or less than 0.1 would be if that line is pretty much completely flat like this. It also takes the Euler, so this rotation converted to an Euler, and sets that slope angle variable. So it will draw debugs if that is sloping local variable is true, and a debug draw input is true. It will then draw some debug things here, a rectangle and a line, and then if draw debug points and input boolean is true, it will draw a transform with a box, essentially, 2 different boxes as well. So all of that, and we have a boolean that tells us whether or not we're on a slope, and a vector that gives us the angle of this slope. These are both used to set global control rig variables, and then the function is called twice. Once from the IK ball right bone, which looks to be just for the sake of doing a debug draw, and then from the IK foot right bone. And that is used to set a character slope angle variable. Next, a boolean sloping and crouching is set from the is crouching input and the is character sloping boolean that was set over here. Next, it does a trace for each foot here with a process foot trace node, which is another function with lots of different math. So let's look at it one step at a time again. We have a sequence here, a branch. Okay, so the sequence has two execution strings lined up to it. We have the first thing we do is we go into a branch, and this is just for debugging. The second thing it does is it goes into a return, which returns three values: a target offset z float, a new hit normal vector, and a did trace hit boolean. So let's trace back this first one, a target offset z. Here we're isolating the z value of a vector, which is the result of a sphere trace by channel. This new hit normal is an interpolated variable taken from this sphere trace if a certain condition is met. Otherwise, if the sphere trace hit anything, actually. Because if it didn't, it just takes a z of 1 and interpolates that, which means a surface that's pointing straight up. It'll make more sense soon, I hope. So finally, this did trace hit boolean, which is the output from a sphere traced by channel. So this node is being connected up to a lot of stuff here. So let's see what it is actually doing. It gets the transform of an input bone. In this case, it's the IK foot left bone. It adds 50 on the z and subtracts 50 on the z, and then does a sphere trace. So the same sort of trace as that previous slope function. And it gets the hit location and the hit normal and whether or not there was a hit. So it gets the location of the floor in relationship to the IK left foot bone, whether or not there is even a floor near the IK left foot bone, and then a hit normal. So the facing direction of the floor. Now, if there was a hit, it uses the hit normal of the trace. So meaning that if the character is not way up in the air, it's going to use the hit normal of the ground underneath the character's foot. And it's just going to do a spring interpolation using a current hit normal variable, which is just going to smoothly interpolate that normal. And that is this new hit normal output. It takes the location, it gets the z of that location, and returns that as a target offset z, because there is no need for the x and y, because all it does to the foot bones is that it raises and lowers them. Finally, we also have, not finally. Looks like those are the three outputs. I'm not sure why, for a moment there I thought there was a fourth one. I do not know why. So, it takes that information, sets a target left foot offset z, which also is a direction because it's going to be a negative or a positive, from the foot to the ground, the normal of the ground underneath the foot, and whether or not there's even a trace hit. So whether or not the foot is even near enough to the ground to do anything. It does the same for the right foot, and that is it for the section that gathers info about the world. Next, it adjusts the rig based on the data that has been gathered. So, the first thing it does is it adjusts the pelvis to bring the lowest foot to the ground. So, when the pelvis moves, it's my understanding that the rest is not going to let me move it here, but because the pelvis bone is the parent in the hierarchy of the skeleton only under the root bone, meaning that when the pelvis bone is moved by default, everything else is moved unless you specifically move something the same distance as the pelvis in the opposite direction, only then will it stay in the same place while the pelvis moves. So, it gets the target left foot offset Z and the target right foot offset Z and finds which one is closest to the ground. And it interpolates that with a current pelvis offset Z. So the pelvis is going to lower to bring the lowest foot to the ground. So that's what this is doing. So it interpolates that to smooth it out so nothing jumps around too much. And then with that smoothed variable, that smoothed value, it sets a current pelvis offset Z variable. Next, it sets the transform of the pelvis control. To do so, it gets the transform of the pelvis in global space, inverts that, which returns negative values, and it's going to rotate this in a given direction. I believe it also moves it in that. Yes. Okay. So it says it rotates the transform in a given direction. And so we have this section here which detects the character's slope and adjusts the pelvis if the character is on an incline to prevent the knee from going into the torso. So it checks whether or not we are sloping and crouching, and if we are not moving. So if the character is not moving and the character is sloping and crouching, then if that is true, it is going to interpolate a variable which is the slope angle. And it is remapping a 0 to negative 20 to 0 to 20. So it is getting the inverse of the slope angle. And using that and adding that to this, to the x value for the transform direction. No. I'm sorry. It's actually adding it to the pelvis offset Z float variable. I misread the graph there. And if this is true, it is also taking a value of 2 and inputting that into the x value here. So the result of this transform direction node is then plugged into the set transform control node, which is setting the transform of the pelvis control. That was a lot, and I personally find this to be fairly confusing. I don't understand how this transform is being inverted, I guess, and how a node that's supposed to rotate a transform can move that transform, can translate it. But it seems like it is translating it somehow, even if I don't fully understand how. And it is using the current pelvis offset. It's doing some additional calculations to determine if the character is on an incline, and if that is true, prevents the knee from going into the torso. But because this current pelvis offset is also in here, it is lowering the pelvis, ergo the entire character down so that the lowest foot touches the ground. Next, it seems like it is also setting the offset transform of the IK foot root bone. Yep, because that is separate from the hierarchy. Moving the pelvis is not going to move it, so it also moves it along with the pelvis. Next, it is processing the left foot offset with a process foot offset function here, which does a bunch of things. We'll go through it one at a time. It does the same for the right foot. So, the first thing it actually does is sets the offset transform of an input IK foot bone, I believe. Yes. And it adjusts the transform by the result of this. So, the first thing it does is it adjusts it. I'm just going to read the comment. Adjust by the pelvis offset. Example, if the foot starts 10 units in collision and we pull the pelvis down by 5 units, we need to bring the foot up by 15 units. So it needs to account for the fact that the entire character has been offset by this pelvis offset variable. So it takes the current offset input and the target offset. I should have covered that. I should have went over this before I went into the function, but we have the current left foot offset and the target left foot offset variables, which it calculated earlier, and the current foot hit normal and the did left foot trace hit as inputs. So it gets the pelvis offset, subtracts that from the target offset of the foot, and if the trace hit in the foot is close enough to the ground, it interpolates the current pelvis offset subtracted from the target offset. If that did not happen, it only subtracts, it only interpolates the target offset. It does not subtract the pelvis offset from it. So the result of that interpolation is then fed into another transform direction, which is putting the offset in IK foot space, I guess. So we get the left foot transform in root space. We don't use global space as the root may be rotating the mesh on top of the actor's rotation. Using this get relative transform, that is then being moved into the IK foot space through the use of these two nodes. Again, I apologize that I don't understand the math or reasoning or logic behind why these two nodes do that. And then it sets the offset transform. So it needs to convert this to this space here. And that is going to move the foot up or down based on the target offset that was input into the function. Next, it sets the rotation of that input control by taking the current hit normal, doing an aim math node again. This time the IK foot root bone is the input transform, and it's rotating the foot bone so that the foot aligns with the hit normal of the ground. It also takes that interpolated value and outputs a new offset z variable, or value, which is then used to set a variable. So coming back up here, I should clarify. So it looks like this is just these nodes here. They are taking this offset. They are transforming it on the z-axis by the current pelvis offset while also converting the transform into pelvis space. I don't understand how it works, but that is simply what this is doing. Additionally, it offsets the pelvis offset by some value depending on whether or not the character is on a slope and if it needs to adjust certain things because of that. I just did want to try to clarify that a little bit. So next, it does the same thing for the right foot as it does for the left foot, and then finally, it applies the IK to the legs. So it sets the transform of the pelvis bone from the pelvis control, which was previously moved here. It also does basic IK on the left foot using the transform of the IK foot L bone. It also uses that pole vector control for the pole vector and uses that thigh and calf length as a part of the calculation. Then it does that exact same thing with another basic IK node for the right foot, and that is finally it for the control rig. So it gets a bunch of data based on whether or not the character is sloping, and data about the slope that the character is on. It uses that to lower the entire character to the ground so that the lowest foot touches the ground. And then it from there it ensures that both feet separately are at the ground and angled accordingly to the ground surface. And that's a lot of nodes, but that is essentially what this control rig is doing. Alright everyone, I hope you enjoyed the video. If you did, be sure to like and subscribe to the channel. A new Locomotion system tutorial series is in the works. It'll be pretty much a revised and completely remade version of the old tutorial series for distance matching in Unreal Engine 4 with a new system with many improvements in Unreal Engine 5. However, it's still in the works. The system is not complete, so it will be a while before I begin posting tutorial videos for it on this channel. Thanks for watching, and I'll see you in the next video.